Hello everyone, welcome back. So we were discussing kinetics, right? And we were discussing the factors affecting the rate of your reaction. And the most, or in general, the usually encountered factor is the concentration of your reactants. The key here is that it's not the products, it's always the concentration of your reactants that define or are going to regulate the rate of your particular reaction, right? Then we also looked at temperature, I believe, right? And then we also looked at how stoichiometry is relevant to your particular reaction or rate of the reaction being related to your individual rates of the different compounds, right? And then I believe we started moving on to complex sets of reactions, let's see, or when you have a complex kinetic model, right? You want to model these later on. So here we started looking at or considered a set of examples. So obviously this is applicable even when you have, let's say, 20, 30 or so reactions now, right? So how would you go about this? Let's say if you have 20 such reactions now. So here you have A and B, reacting to form C, and again I guess C and A reacting to form B, and so on, right? How do you go about it? So let's look at that, I guess. So first aspect is to write down rate of reaction 1, and what is that, I guess? So what do you know it's going to be? And let's say it's the rate constant is K1 and K2. So rate constant is 1 and 2, right? It's going to be K1 times concentration of A times concentration of B raised to the power of 2, right? Yes. And what about rate of the reaction 2? That's going to be equal to K2, the rate constant, into concentration of C into concentration of A raised to the power of 2. So that's what we have here, right? But here let's say I'm not concerned with the rates of the reactions. I want to know how A, B and C change with respect to, let's say, time. How do these concentrations change with time now? For that I need to be able to know or model the relevant rates of the reactions. Now what is R net of A, R net of B, and same case R net of C, right? So first obviously I am going to try to use these three, or express them in terms of rate of loss of A and obviously rate of formation of A. What is R net? Obviously I guess, and again same case, R net of B will be equal to rate of formation of B minus rate of loss of B, and again R net C will be equal to rate of formation of C minus rate of loss of C. So let's see what it is we have here, I guess. So let me have same nomenclature here, right? So equal to rate of formation of A minus rate of loss of A, and let's see how we can relate them to your relevant rates of reactions 1 and rates of reactions 2, right? So let's look at that, I guess. So how is A being formed? It's being formed nowhere, so that's going to be 0, right? Minus rate of loss. How is A being lost? It's being lost by both the reactions. So what is that, I guess? So we are going to have minus rate of reaction is 1 because the stoichiometric coefficient is 1 here, and minus 2 R2, right? Hopefully that makes sense. Yes. So or it's just minus of R1 plus 2 R2. So anyway, A is not being formed, it's only being lost due to both the reactions, and as we looked at earlier, rate of the reaction is equal to what now? Rate of, let's say, loss of A by its stoichiometric coefficient, right? This is what we discussed in the last class, and that's where we get these particular aspects from, right? The rate of your loss of A, and that's what we see here. And so let's move on to B. Let's look at how B is being formed. B is being formed from your second reaction. Stoichiometric coefficient is 1, so it's going to be rate of reaction number 2, right? Minus, how is B being lost? It's being lost to the first reaction, and what's the stoichiometric coefficient here? 2, so it's going to be 2 R2, right? And again same case, pardon me, not R2, it's obviously R1. Again, so B is being formed by reaction 2, that's what we see here. Yes, and the stoichiometric coefficient is 1, so that's R2 there, just R2 1 into R2, and how is it being lost now? It's being lost through the first reaction, and it's 2 times because its stoichiometric coefficient is going to be 2, or is 2, pardon me. And same case with R net C, rate of formation of C. How is C being formed? It is being formed in the first reaction, right? And what is the stoichiometric coefficient there? It's 3, so 3 R1 minus, how is it being lost? It is being lost by the second reaction, right? And the stoichiometric coefficient is 1. So that's what we have here, right? So if we just simplify that here, minus R1 minus 2 R2 is equal to minus 2 R1 plus R2 is equal to 3 R1 minus R2, right? So in general, what are we, or how are we going to express these sets of equations as? We are going to express them as matrices. R net matrix is equal to the relevant coefficient matrix times of the rates of the reaction matrix, right? So R net will be what now? The matrix that has R net of A, R net of B, and R net of C. And what is A going to be equal to, I guess, right? You are going to have the relevant coefficients here, and what are they? Minus 1 and minus 2, and what do we have here, I guess? Minus 2 and plus 1, and here we have 3 and minus 1, right? And here we are going to have your R1 and R2, right? Yes. So I believe now with this, let's say you can set it up in your particular what do we say, MATLAB or such, and once you can have this matrix with respect to relevant models, right, you can go ahead and get this done. So here we are just looking at how to express the R net in terms of various reactions here, right? So that's what you see here. So again, let's move on. So the next major aspect that we are going to consider is reactors, right? And let's first see what's the relevance here. And so this is going to be one of the fundamental aspects you are going to learn throughout the course of your class now, right? So let's take some time about understanding the relevance of the reactors to our particular case, or the environmental engineering here, right? And then look at what are the different reactors we come across, and then we are going to look at how to model them, right? So let's look at some cases now. Let's say there is an industrial what do we say, estate near Haridwar, and I am at Roorkee, I think maybe 30 kilometers downstream, right? So let's say some industry there, let's say I am going to use the slide here. So here we have Haridwar, and here we have Roorkee, and let's say some industry is dumping its waste, right, into the Ganga canal or Ganga here, let's say, and the Ganga canal or Ganga is flowing downstream. So I want to know, let's say the concentration is C naught here, let's say, or let's say concentration of, this is the toxic compound A naught, and what is it at Roorkee though? This is what I want to know though, right? So how do I go about it? So for that, you know, I am going to define a reactor of a certain what do we say, boundaries, and then I am going to model A, or how is A going to change or transform with this, within this boundary, and by that what do we say, once I am done with that model, and I also consider some assumptions, I guess, to make the model relatively simpler, right, I can end up calculating or predicting the concentration of this particular compound or toxic compound A at Roorkee now, right. So another example is, let's say I am in this particular room, let's say, and I am looking at air pollutant, let's say, and someone usually burns crops here, let's say, and let's say the wind blows air in, let's say instead of a door here we have another door or window here, right. So the wind is coming in and it's going out here, so an air pollutant is also being transported along with the wind. But let's say you have a filter or such here, let's say, you know, let's say you have a plant that can degrade this toxic compound. This is a hypothetical case, pardon me, right. So you want to model what is the concentration of this compound in this room now, right. So for that you have the relevant variables, you can plug them in and then come up with how will this concentration change with time here, right. Here you are checking how is your concentration changing with distance. In this particular case, or the second or latter case, in this with respect to room, let's say where the air pollutant is flowing in through the door and flowing out through the window, and maybe some reactions inside the room are degrading your compound or even leading to formation of your compound, you are looking at how the concentration profile changes with time. You can also look at how it changes with distance, but that is going to be a relatively more complex system, right. So anyway, or even let us say, you have your activated sludge process here, right. You have your activated sludge process coming in and going out. So you want to know how the concentration before it reaches steady state, let us say, or what is it going to be at steady state, or before it reaches steady state, how is it going to change with time, right, and so on now. So for these aspects we always need to be able to define the relevant reactors. We are going to see what are the ideal case reactors. So this is an example of your activated sludge process. I want to know the concentration either at equilibrium or more specifically how it changes with time in my activated sludge process, right. I want to be able to use this concept of reactors and then model concentration versus time, and so now I know that at equilibrium this is the concentration that is going to be, and this is going to be my design variable, right. So this is what we are going to look at. So reactors, again, they are relevant everywhere. So there are 3 ideal case reactors. Let us look at what they are. So the first one would be a batch reactor, and keep in mind these are just terms that we are assigning to different scenarios. So let us look at what they are. The first case would be a batch reactor. So it is a closed system, right. Keep in mind that it is a closed system, no flow coming in, no flow going out and such, but the assumption is that it is completely mixed. This is the symbol I am going to use for saying that the system is completely mixed. So batch reactor is one that is a closed system and that is completely mixed, right, no flow coming in or going out. And the second phase is a plug flow reactor, plug flow reactor. Right, similar to flow through a pipe, let us say, right, or a channel flow. So the atoms or molecules enter here and there is no mixing here, right. So the concentration changes here with each distance or with distance, I guess, right. So there is no longitudinal mixing, only lateral mixing, right. The concentration changes as we go along. So if I draw a graph of C versus x, x being this particular distance, it can decrease, it can increase, or so on, right. So here this is a case of plug flow reactor. Obviously what can you what do we say use this to model. So if you have a canal, the thing that we just talked about, the example, so Ganga canal, so I have Haridwar here, I have Roorkee here, and I have the flow coming in, going out, and I can use the plug flow reactor model concept to look at or model how is the concentration of a particular compound going to change between Haridwar and Roorkee, right. So this is one example for plug flow reactors application, but obviously we will be having relevant assumptions, right. And the third case which people usually come across is the completely mixed flow reactor or continuously stirred tank reactor, right. So completely or completely stirred tank reactor, right. So you have 2 cases more or less the same. So in general what is it about now? So you have flow coming in, you have flow going out, right. It is not a closed system, that is the whole aspect here, and you have obviously it is completely mixed or continuously stirred, I guess, continuously stirred. So again you have complete mixing continuously, right. So that is what this is the scenario that you need to conjure up whenever someone refers to CSTR or completely mixed flow reactor. So what can we approximate by using this reactor? Let us say you can say a lake, let us say a lake, yes, but obviously there are a lot more assumptions involved here, right, especially with respect to mixing. You are going to have issues with respect to diffusion and advection. We are not going to go into that in greater detail, but in the engineered systems what can you use that, I guess, any of your unit process, right, your ASP, SBR and so on, what are they more or less? All of them are having continuous flow coming in and going out, or at least ASP, pardon me, will have continuous flow coming in and going out, and you will in general have continuous mixing here, right. So you can use the concept that we are going to later on look into with respect to CSTR whenever you model your engineered systems. So obviously whenever you come across a scenario, you will need to be able to identify which class will that be under. Is it a batch reactor, a plug flow reactor, or a continuously stirred tank reactor, right? And so then we can take that through. So let's move on to why or how we can model the concentrations. So for that aspect, we need to talk about mass balance or material balance, mass balance or material balance. Right, and this is again a fundamental aspect here, so which we are going to use whenever we are going to look at modeling various reactors or compounds within a reactor, right? So what I guess, where is this from? So we know that the material is conserved, it's neither formed nor destroyed, right? So more or less that's the case here. So let's look at some of the applications here, right? So in general there is a fundamental equation here, dC, or change in concentration with time, plus the del product of the flux is equal to the sources and sinks. So D is the this is the del product, right? And that will give me an idea about dou by dou x, or how is that particular variable changing with each of the dimensions here, right? Whenever I say this, that more or less translates into dou by dou x of the particular flux here, in this case dou by dou y and dou by dou z. How is flux changing with with each dimension there? And J is the flux, and flux in this case is going to be what now? Mass per area per time, okay? Changing the mass of that particular compound, let's say per unit area per time, that's more or less flux, right? And then what else? S is the source or sinks of that particular compound, sources or sinks. So keep in mind that this is the fundamental equation. Everything else that we are going to look at is going to derive from here, is going to be derived from here, right? So in general, in flux there are two cases. One is advection, the other is diffusion. We will not go through this in detail because this is outside the ambit of the course, but it's worth understanding what it is about. So for example, let's say I'm trying to now help you understand advection. Let's say you know, have a highway here, right? And my house is right here. Yes, I have a dust particle here that's what do we say, suspended over the road, let's say. And if there is wind blowing, let's say, the wind is going to carry the dust particle to my house, let's say maybe 100 meters down the or perpendicular to the road, or so on. So whenever there is a net fluid motion, let's say in a direction, net fluid motion, right? So then I can say that, you know, a particular what do we say, advection can or is an important transport mechanism, right? Is it important transport mechanism, right? So that's the case here, though, advection, I guess. The other example I want to have is here, let's say this is the recording session or class here, and so I am here at this podium, right? And let's say there are a couple of students sitting here. There are no fans running, so there is no fans, no wind blowing. This is a completely sealed room now. But if I open a scent bottle here, let's say, you know, I open up a scent bottle here now, let's say. So after a certain amount of time, the students sitting here, right, this is the plan view obviously, can sense or, you know, smell this particular scent or the compound. Why is that now? Because due to difference in concentration gradients, or the concentration gradient, pardon me, and due to diffusion, the compound is going to be transported from, what do we say, my podium to the students here. And why is that? Because of concentration gradient. And keep in mind that diffusion is random, so it always flows from higher concentration to regions of lower concentration. Anyway, that's good enough for now. We won't go into that in greater detail, right? So we still have dC by dt plus the del product of flux, that's a vector there, I guess, right? That's something that needs to be corrected there. And so we say that the flux can be due to both advection whenever there is a net flow of fluid, and due to also diffusion, which is random, and due to concentration gradient, and that is equal to what now? The velocity here, and then obviously the concentration of your particular compound plus the diffusion coefficient here, D is the diffusion coefficient, into del product of your concentration here again. And this is going to be negative because the diffusion takes the concentration away from higher region to lower region, right. So here it is negative, I guess. This is a negative here. Yes, this is what we see here, right. So again the del product here, if we put that in dc by dt and plug that in, I guess, plus del, assuming that the velocity is constant or does not change with dimension, let us say. So del dot c is equal to d del square c plus sources or sinks. So this is your final equation here. So what does this? So let us look at what each variable gives us an idea about. This tells us how the concentration is changing with time, the first set of variables, or this dc by dt, and u del c gives us how is advection affecting your system, right, the transport of a particular compound due to your system, and this particular set of variables relate to diffusion, right, and this with respect to sources or sinks or any rates of or reactions leading to forming your compound or loss of your compound and so on, right. So again let us look at what we have here. The first variable here, dc by dt, or set of variables, the differential here is about giving us an idea about how the concentration is changing with time or accumulation of your compound, right. Can be negative 2 obviously. And the second set is going to give an idea about advection, let us say. If there is a net fluid flow, how is that going to affect the transport of your particular compound? This one is going to be due to diffusion and sources or sinks. Anyway, this is outside the ambit of this course, so we are not going to use this in greater detail, but the next equation which is derived from this is going to be the case. So in this equation we are going to neglect diffusion, okay. We are going to neglect diffusion, which is the case in most engineered systems in environmental engineering, not in natural systems, keep that in mind, right. And so we are going to end up with V dc by dt is equal to q in C in minus q out C out plus volume into rate of formation of the compound minus rate of loss of the compound. So let us see what we have here. So more or less if you multiply this particular equation by V and then neglect diffusion and take this advection term to the right hand side, this is what you end up with. So again if we just multiply our previous equation with volume of your system, right, previous equation as this fundamental equation with volume of your system, and take the advection term to the right hand side and then neglect diffusion and then expand upon the sources and sinks, this is what you end up with, right. So let us see what we have here. What does this variable give you an idea about, or this set of variables, I guess they give you an idea about accumulation, I guess. So overall change in mass of your particular compound in that particular system boundary with respect to time, right, that is what you see in this particular set of variables. And what is this giving you about? Q in, what is Q in? Flow rate coming in, Q out, flow rate of your water solution compound going out. Cn is the concentration of your compound at the inlet. C out is equal to concentration of your compound at the outlet, right, and V is your system volume, RF equal to your rate of formation rate of formation of your compound, RL equal to rate of loss of compound, right. So, again what do we have? Qin is the flow rate coming in at the inlet, Cin is the concentration of your compound at the inlet, C out is the flow rate going out of your system, and C out is the concentration of compound at the outlet, V is the volume of the system, RF is the rate of formation of your compound, and RL is the rate of loss of your compound. So, let us see in great detail what these are about. So, what is our fundamental mass balance equation? V dC by dt is equal to Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss, right. This is what we have. So, let us understand what each of these sets of variables help us understand, I guess. So, this is the accumulation term, right, and this particular equation, what is this? Q is what do we say, volume per time, let us say the units, and what is concentration? It is mass of your compound per volume of your what do we say, solvent here. So, that more or less means it is equal to mass per time. So, that particular set of variable gives you an idea about mass coming in into your system, right. So, what is Q and C in idea, giving you an idea about the mass coming in or flowing into your system. So, that is what you see here, and same case Q out C out will again be mass per time, but this will give an idea about what is the mass flowing out of the system now, right. So, this is the mass coming into the system, this is the mass flowing out of the system, right. So, this is what we have, and what do these terms give us an idea about? V is volume here, and what is rate? It is mass per volume per time. So, what will that come out to be? That is going to be equal to mass per time, again same units as you would see there, right. So, this will give you an idea about the formation or loss of your compound, right. And this obviously again what is this equal to volume into concentration is mass per volume, and the differential is per time, right. So, that is again equal to mass per time. So, all the units are more or less mass per time as you see, right, and this gives us an idea about how is your compound either accumulating or being overall accumulation of your particular compound in the system. This gives you an idea about how is the mass flowing into the system, and this gives you an idea about how is the mass flowing out of the system, or not how much, I guess, and this set of variables will give you an idea about how much of it is being formed and how much of it is being lost with respect to time, right. So, I believe we are almost out of time. So, let us quickly review what we discussed. So, we discussed, I guess, batch reactors and plug flow reactors and continuously stirred tank reactors. Batch reactors usually used in the lab, plug flow again lab or engineered systems or natural systems like rivers, CSTR either lakes, right, or most of your ASP or most of your unit process, right. And for all these cases we looked at the relevant conditions, how to describe them, and then we looked at the fundamental mass balance equation, and then looked at the generic equation we are going to use throughout the class. It is V dC by dt equal to Qn Cn minus Q out C out plus volume into rate of formation minus rate of loss. So, how is the compound changing with what do we say, time in your system? It depends upon the mass coming into the system, mass going out of the system, and then how is it either being formed or lost due to various reactions. So, in the next class we are going to apply this mass balance to each of these three reactors here, or reactor systems, I guess. So, I guess with that I will end the class for this session, and thank you.